Hey guys, in this tutorial we are going to cover dynamic programming. So basically dynamic programming is a technique which is used to optimize plain recursion. So in this tutorial what we are going to cover is we are going to create a program that basically make use of recursion, and then after that we are going to use dynamic programming to see and to optimize the plain recursion. So we will basically see how some recursive solutions are not optimized. So let's start with this. So the problem is, let's first consider the Fibonacci numbers. So if you haven't heard of Fibonacci numbers or the Fibonacci series looks like this. First number is 0. The second number in this series is 1. So the first two numbers in this series is fixed. So the third number is calculated by adding these two numbers or by adding the previous two numbers, right? So when we will add these two numbers, we are going to get 1 here. So when we want to calculate the next number, we will have to calculate the previous two numbers, which is 1 plus 1 equals 2. To calculate the next number, we will have to calculate 2 plus 1, which is 3. And this series goes on and on like this. So our task is to write a function which will return or which returns the Fibonacci number at a particular position, at some position, and we are going to specify this position at the time of function call. So our task is to write a function, and basically this function is going to use recursion. So we are going to use recursion to implement this function. So the function call will look like this. So this is basically the function call, and as you can see that in the function call I have provided a number. This number represents the position at which we wish to return the Fibonacci number, right? So in this series you can see that this is the 0th position, then 1, 2, 3, 4, 5, 6, 7 and so on. So the Fibonacci number at the 5th position is 5. So how can we calculate the Fibonacci number at the 5th position? So now I'm going to write the implementation of the function, which is basically going to use recursion. So using recursion, I will write this function. Since it will return a number, which is basically the Fibonacci number, I'm going to write the return type as integer. Then fib is the name of the function, and let's suppose the position is marked as n. So whenever we will pass the, let's suppose I make a call to the Fibonacci function as this one, so the value of n will be equal to 5. So we are going to pass the value at the time of function call to this function. Alright, so let's discuss something about recursion. So if you don't know about recursion is basically a function calling itself. So let's suppose I write a function like this, and in its body, if I will again make a function call to the same function sum, it is basically going to call this function again, and then this sum function will go here, and this goes on, and this is basically known as recursion. So recursion is basically a function calling itself. as you can see that in this example, this will go on till infinitive. So we will have to specify some condition over here to stop recursion at some position. So that is what we are going to do in the first step. So in the first step, we are going to write a condition that if the value of n, which means the position, is less than or equal to 1, then we are going to return n. So whenever this recursion is going on inside this function, we will write the recursive call here, but if the recursion will again go here, it will first check the condition. If the condition evaluates to be false, then it is going to if this condition is going to return true, then this will return the number n. And you can see that if n is less than or equal to 1, which means that the value of n can be 1 and it can also be 0, which is less than or equal to sign, as you can see here. So at this position, you can see that when n equals to 1, the Fibonacci number is same as n. You can see that these both are same. That's why we are returning the n. So let's suppose the user gives a number 1. So this will check the condition. So since the value of n is equal to 1, it will return 1. And since the Fibonacci number at this position is 1, this is the correct procedure. And similarly, it holds true for 0 also. So this is basically the condition that stops recursion. So this is basically the condition that will stop recursion. So let's suppose I want to calculate the Fibonacci number at 5th position. So if I want to just get this Fibonacci number at this 5th position, I will first have to calculate the Fibonacci number at the 4th and the 3rd position, and then I will sum them up to get this number. So you can see that the Fibonacci number at 3rd position is 2 and 4th position is 3, so I will just add them up to get Fibonacci of 5. So now we are going to return. So now we are going to make a call again to this Fibonacci function, but now instead of 5, we will just pass the previous number, which is written as n minus 1, and we will add the previous to previous one, which is this one. So this one is n minus 2. So at this step, we have made a recursive call to the Fibonacci function. As you can see here, this is the Fibonacci function, and this is also the Fibonacci function. So this is the plain recursion that we have shown here, and you can see that how this function will work is, first it will call the Fibonacci number at the 4th position, then Fibonacci number at the 3rd position. Then it will call the Fibonacci number at the 1st and 2nd position, because if you want to calculate the Fibonacci number at 3rd position, you will have to first calculate the previous two numbers. So if you want, for simple explanation, I'm going to draw a recursion tree here, which will show how this recursion is going on. So here is the recursion tree, which basically represents how recursion is working in case of our example. So the call is Fibonacci of 5. So we want to calculate the Fibonacci number at the 5th position. To calculate the Fibonacci number at the 5th position, I will first have to calculate the Fibonacci number at the 4th position and the Fibonacci number at the 3rd position. And then I will have to add them up to get Fibonacci of 5. But as you know that in our example we only know the beginning of we only know the first two numbers, which is 0 and 1. We don't know Fibonacci of 4 and Fibonacci of 3. So we will also have to calculate the Fibonacci of 4th. To calculate the Fibonacci number at the 4th position, we will have to calculate the 3 of Fibonacci number and 2 of Fibonacci number. So you can see how recursion is working. This function makes a call to these two functions, and then again this function will make a recursive call to these two functions, and this will go again in this step. To calculate the Fibonacci number at the 3rd position, I will have to calculate the Fibonacci number at the 2nd and the 1st positions. As you can see here, to calculate the Fibonacci number at 2nd position, I will first have to calculate the Fibonacci number at 1st and the 0th position. And here we know that the n is equals to 1, so this is basically going to return n, so the recursion will stop at this step. And at this step and at this step. In these three steps, we know that the value of n is less than or equal to 1, so the recursion will stop here. And then you can see here it will go here, Fibonacci of 3. To calculate the Fibonacci of 3, we again have to calculate the Fibonacci of 1st and 2nd. And similarly, here also we will write Fibonacci of 1 and Fibonacci of 0. So at this step also, this recursion will stop. When the recursion stops, now it is going to trace back and it will add the Fibonacci numbers. So Fibonacci number at the 1st position is 1. So 1 plus 0 is equals to 1. So 1 plus 0 is equals to 1. So Fibonacci of 2 will be equal to 1. Fibonacci of 1 is 1. As you can see at this step, it will just return the position. So Fibonacci of 1 will be equal to 1. So 1 plus 1 will be equal to 2. So 1 plus 1 equals to 2, but it is stored at the Fibonacci of 3 number. So at the 3rd position you can see it is 2. Now Fibonacci of 2 will also be calculated as Fibonacci of 1 and Fibonacci of 0. So this step of when recursion will stop, this step will again go upwards and it will start adding these two blocks, these two children of this root, and then finally we will get the Fibonacci of 5th number. So this is basically an example of plain recursion. So now we are going to use dynamic programming to optimize this problem. So now we know how this function is working, we know how recursion is working, we now know how it is actually producing the result. So let's see in this recursion tree how can we optimize this problem. So at this step you can see that I am calculating Fibonacci at the 3rd position, and for that I am calling Fibonacci of 2 and 1 and again this. So you can notice here that at this step we are repeating this step in our program at this step also. So you can see that this program is not optimized. Because we are doing the same step again in the same function. So we can do something to actually just make sure to optimize this whole problem that is occurring in this problem. You can see that similarly Fibonacci 2 is calculated here, it is again calculated at this step and at this step. So there are so many duplicate recursive calls, and this makes this program not optimized. So we are going to use dynamic programming now to resolve this whole optimization problem. So what is dynamic programming? So now we are going to use dynamic programming to optimize this problem. So let me first define what is dynamic programming. So the very basic idea of dynamic programming is to store the results of the subproblems so that we do not need to recalculate it again. So what is a subproblem? The problem is to find the Fibonacci number at the 5th position. But we know that in order to calculate the Fibonacci number at 5th position, I will first have to calculate these two numbers. So this is the main problem, and all these are the subproblems. So this one is a subproblem, this one is again a subproblem, and all of them are subproblems. So in this problem you can see that this subproblem is occurring again. So we are actually recalculating it again and again in the same program. As you can see that we are using Fibonacci at 5th position. Let's suppose the user at Fibonacci of 500. So that will make so many recursive calls to these subproblems which are occurring again and again. So it will take a lot of time to calculate these subproblems. So what we are going to do is, whenever we solve a subproblem, we are going to store it in an array, and this array is known as lookup array. So lookup array is basically a simple array. It is used to store the results of the subproblem. So how does it solve our problem of optimization? How does this dynamic programming, which is this thing, how it solves this optimization problem? So the answer is that whenever you will calculate a subproblem, you will store this result in an array. So let's suppose this is Fibonacci of 4, 0, 1, 2, 3, 4. So whenever we will calculate this subproblem, we are going to store this in this array whenever we have just calculated it. So whenever the next time we are going to encounter the same subproblem, we are first going to look up in this array. That's the very basic meaning of lookup array. So whenever a subproblem occurs again and again in the same problem, we are going to look up in an array. If that problem is solved here, then we are just going to replace this whole thing with the result. So initially the strategy will be to initialize all the values as 0. So whenever we will solve any subproblem, we will see that if it is 0 or not. If it is 0, we are going to calculate it, and whenever we calculate it, we will just overwrite these values. So whenever the Fibonacci of 3 is required again, we are not going to solve it again. What we will do is we will just look up in this array, and since the position is not 0, the number is 0, here you can see that it has been overwritten as 2 because we have already calculated it before. So whenever this subproblem will occur again, we are not going to calculate it. We are just going to write this value and we are going to replace it here. So this is how dynamic programming solves the optimization problem. So if you're using a plain recursive method like this, and if your subproblems are occurring again and again in a subproblem, basically there are many problems which are there which uses recursion, and this problem of recalculating the subproblems occurs again and again. So dynamic programming was used to optimize this problem, and the strategy is basically very simple. We will just create a lookup array, or we can create any other data structure, and we will store the results of these subproblems in this array. So whenever we are going to calculate a subproblem, we are going to store the results in this array, and whenever the next time this problem will occur again in the recursive tree or in the recursion step, we are just going to insert the value here. So we have written the Fibonacci function using recursion. Now we are going to use dynamic programming approach. So I'm going to write here the program which will use this approach. So now we are going to write the dynamic programming program which will basically solve this whole problem. So first of all, it will be integer Fibonacci number, and the position is int n. So now what we are going to do is, first we will create a function. Let's name it int f, and let's say we are going to only use 50 Fibonacci numbers, so I'm going to create an array of 50 integers. So this array has the capacity to store 50 integers, and this function will basically, initially I will just write a for loop which will run from int I equals 0 position till I less than 50, less than equal to 50, sorry, less than 50, then plus I, and I'm just going to write here f of I equals to 0. So this for loop, what it is going to do is, it is going to initialize our whole array with 0 values. So the function, sorry, the array will look like this till 50 times. So initially we have just initialized it as 0. So whenever we want to we will just overwrite the values of these index position, and then since we want to return the Fibonacci number at the nth position, we are going to return f of n. So let's suppose initially it was fib of 5. So this is the function call. So the value of n is equals to 5. So now what we want to do is, we will do the steps here which will basically override the value at nth position. So if this is 0, it will override this value with the Fibonacci number when after calculations. So it will be 5, and then we are just going to return f of n. So now let's write the calculations. So here I am going to calculate the Fibonacci number at any particular position. For that I am going to use a for loop which will run from int a equals to j less than n, and we are going to increment the value of j. So initially we know that the first two numbers in the Fibonacci numbers are fixed. We do not need to recalculate them. So after this step, I am just going to write here the Fibonacci number at the 0 position is equals to 0, and the Fibonacci number at the first position is equals to 1. So this is the first line, this is second, and this is the next step. So when I will write this line, it will basically This is 0, 1, 2, 3, 4, 5 and so on. So it will basically override the first two values since we already know them. So we want to calculate the Fibonacci number at the fifth position. So this for loop is going to iterate over 2 and it will reach till the nth position, as you can see here. So n equals to 5. So this for loop will iterate from 2, 3, 4 and 5. So at each step what I'm just going to do is I'm going to store the j position is equals to f of j minus 1 plus f of j minus 2. So this is the calculation that we are going to do. So let's see how this actually works and how does it solve this optimization problem. So initially we have just created an array with 50 integer values it can hold. Then we have created a for loop which will initialize all the values as 0. Since we know that the Fibonacci number contains the 0 and 1 position are 0, so we have done in this step. The next step is the calculation. So we are going to iterate from this position, which is the second position. Since we have already calculated these two positions, we do not need to recalculate them. Then we will move from the second position till the nth position. At each step I'm just going to add, I'm going to store. You can see that this is basically storing the results of subproblems. The results of subproblems. So this is basically dynamic programming. You can see that this is a subproblem. F of j is a subproblem. You can see that first the value of j will be 2. So f of 2, which is basically fib of 2, will hold the value of f of j minus 1 plus f of j minus 2. So first the value of j is 2. So 2 minus 1 equals to 1. So f at one position, you can see it is equal to 1. And f j minus 2, so j is 2, so 2 minus 2 will be 0. So this will be 0, this will be 1. And we have already written this at this step, which is an important step. And then we are adding these two values, and whenever we will calculate any subproblem, we are going to store this value using this assignment operator. So 1 plus 0 will be equal to 1. So f of 2 will be equal to 1. So this step, at the first step or the first iteration, will give f of 2 equals to 1. So it will override 0 and it will write it as 1. So now the value of j will get incremented. So now f of 3 is there. And as you can see, these are basically the subproblems. So whenever we want to calculate f of 3, this will be the sum of f of 2 plus f of 1. Like this. So we do not need to, if you will see at this step, f of 2 is basically 1 because we have already calculated it. So we do not need to recalculate it because we have already done the calculation and we have stored it in this array. So that's the very basic fundamental of dynamic programming, which is to store the results of the subproblems. So now you can see that we are not recalculating f of 2 because we have calculated it in the first step and we have stored it in our array. So f of 2 will be equal to 1, and we have already written f of 1 as 1. So 1 plus 1 will be 2. So f at third position will override and it will be 2 now. So this will go on, and this procedure goes on and on. It will keep overwriting the values and it will keep storing the whole results in our given array. So this is how dynamic programming works, and I've just given a Fibonacci numbers example, and I've shown you how to store the results of the subproblem and how it actually optimizes this whole step. We are not going to calculate it again and again. So this is how it will optimize our whole problem. You can apply the same concept in a lot of problems. So there are a lot of problems in dynamic programming that can be solved and that can be optimized, or it can provide much better solution, much optimized solution than recursion. So in the next tutorial we are going to study the next problem, which is the subset sum problem. So which is the subset sum problem. First we will implement this problem using plain recursion. Then we will see how we can optimize it using dynamic.